All right, Keith is going to give us an update on radiology.
Well, yeah, a little bit. First couple of notes. A, I'm not the smartest guy in the room. Don't pretend to be. No charts, no nothing. And two, I'm the only thing that stands between you and lunch. So that's the most important piece. So I'd like to take a few minutes. AI, and by the way, wherever Rick is, I don't know where he is, but thank you for doing an intro to my presentation. I appreciate it. AI really is in a position to transform healthcare as we know it. There's a lot of things that humans do very well, but there's a lot of things that machines can do better or can do at least as well. And we all look at AI, you think about maybe faces in a crowd. We can all pick those faces out. Machines can do it faster and better. But we're not as good at using computers to identify signs of tumors, heart defects, lung defects, and so forth. So down in Austin, we have an AI innovation lab. And in that lab, we have really shown a dramatic potential for using AI in healthcare. And I'd like to thank Intel. Was in here. A, I'm following him again, but B, with the support of Intel, we've been able to do this. So we're looking at right now detection of pneumonia, emphysema, and alone those two diseases kill about 60,000 Americans every year. So to help with early diagnosis of that is one thing that we're trying to work with the healthcares. At Stanford University, they developed a system called ChecksNet, and it scans x-rays and gives you the probability that pneumonia exists on that x-ray. Well, our AI lab has taken that a little step further, and what we've done with that is taken that network, expanded on it, and our models have now outperformed the baseline test in 10 or 14 categories with that. We use doctors' opinions, and we use 10,000 examples to set the baseline. So one of the things we used is, and I'm going to get this wrong, maybe I have to read it, convolutional neural network. And for those of you who know what it is, that's fine, but for those of us like me who didn't know what it was, it's basically a network that splits the images and the instructions and puts them on individual nodes in a cluster. It does all of its processing on that, then it sends all of that information to a control layer. Control layer aggregates the information and then sends it back to the processing nodes to get ready for the next pass on it. So the thing about CNN, though, we found out obviously that it can handle a large number of pieces of information, okay? And it can do this because it splits that information into, again, multiple nodes. So what we've done then basically in our lab is one of the things, we're Dell. One of the things that we do is worry about cost efficiency. We've done that for years, and our AI and innovation lab, no exception to that. So they look at the cost efficiency piece of that as well too. Now typically CNNs are built with CPUs and GPUs, but we looked at that in a cost efficient way to say, okay, let's use the CPUs, not necessarily any of the expensive GPUs. So using that, we looked at a single Xeon scalable processor. We got about 80% accuracy on determining emphysema. So that is, if you think about it, that is slightly better, really, than human radiologists. And they've been experts at it for years. So The issue was though, that took it took several days to actually come up with that result. That's not acceptable. You don't want to go to the doctor, take the test, and say, come back in 5 days. We'll let you know then. So that's just not an acceptable performance level. But what we've done with this accuracy is we've taken it a step further. Again, the process that we used in our AI Innovation Lab allows us to look at different processors, different memories, different configurations, different nodes, and so forth. Dual processor nodes, 4 processor nodes, whatever the case may be. So we developed a system that was optimized to do this type of work, to do this type of modeling. And the results like this. We're a server company, we got that, okay? So we put more servers behind it. Who would have known that? So anyway, we proved with that modeling that we can go from 4.5 days to just under 11 minutes. How would you like to go to the doctor's office and find out your results in 11 minutes? And then the doctor being able to start that treatment right away instead of waiting for days. What about a child's cancer? Going in there and waiting days to determine what type of cancer it is. Why not know that right up front? That's the direction we're headed from. It's to make these things easier and save lives. That's what it boils down to. We got to an accuracy, believe it or not, of 90%. That's unheard of. Again, the human radiologists are about 80%. So are we perfect? The answer is no. Are human radiologists perfect? The answer is no, but we're striving to get there. What we're really wanting to do is to help the healthcare professionals do their job better, not so much to do their job. We're not intending to take their job away from them, but we want to be able to help them do their job better, more efficiently, and be right more times than not. Any questions? I got us back on time, by the way.
Great, amazing. So beyond emphysema and what you're working on here, where do you see, do you see this as like an appliance that would be shared by doctors? What's the actual implementation? Like, how do you get this to market?
Well, that's where we're headed for. Okay, not necessarily a small appliance, but a larger one. Again, what we did was to use off-the-shelf components. We didn't do anything special. Everything we did was just normal hardware. Even the software we used during this modeling was free open source software. So we're trying to make this available. And we want to get into not just the lung, heart disease. And again, we're not doing it alone. We're working with Intel, we're working with some of the doctors, I was told, are, shall we say, seasoned. And they like the idea of getting better results faster for their patients. So yes.